Thank you, Carolyn. That's right. Please join us on the rooftop. If you don't like my presentation, you can potentially throw me off of said rooftop. As Carolyn said, I've been primarily a data architect. I put a handful of slides for us together today. I don't know if you folks have noticed, but there's been a bit of a buzz around AI lately. It's weird, right? Everyone's talking about AI. I want to talk about the data. I want to talk about structure. Because there is most definitely an AI gold mine and an AI gold rush happening right now. And I think what we're really not focusing in on right now is data and data structure. We're kind of looking at the shiny object of AI, not realizing that the data has to come from somewhere. So this is really what this presentation is going to be, kind of a data architecture perspective, bit of a brain dump from me. So everyone wants AI, boards of directors, C-level. And this is wonderful because AI is like the automated machine on the shop floor. We can exploit it. We can have it do things for us in so much less time than humans can do. But to scale it, that means we need a couple things. We have to put it into applications. I can't just have an AI model that doesn't actually work within an application and create some kind of outcome. So a couple things that we need, the app and the AI software components, they have to have interoperability and compatibility. They need to work well together. And really what that means, if they need to work well together, then that really means that they must operate with a common corpus or a corpus of shared data. The applications and the AI components really need to work with the same data sets at some point. If I have data that looks like this when it's 5 seconds old and it looks tremendously different at 5 weeks old, we've got some discrepancies that we have to work out. And this is really what I want to tackle today is really how do we scale AI from a data structure perspective. And so when we talk about structure, we really are talking about a single cohesive application and data strategy. And that really means, in my opinion, that we must manage complexity well. Our application and data and AI strategy, whatever we call that, enterprise data strategy, we have to be able to manage complexity well. For the foreseeable future, we're going to be dealing with far more data, far more complicated data, and we will just forever be surrounded by complexity. And so we're going to need to manage that complexity. In order to be able to do that, we also need to have flexibility. And so we know that, like right now, does this sound familiar? We've got some applications that are generating some data pipelines that feed data into an enterprise data warehouse. You've got data scientists that are reading that data from the data warehouse. They're copying that data, they're putting into machine learning features into some other environment. They're training machine learning models from that. And you go through this whole gauntlet. You get this model trained, you put it in production. 6 months later, somebody changes something in one of those transactional sources, and the pipeline of data that goes from transactional to the warehouse, to the features, to the model, it breaks, and pardon my French, but all hell breaks loose inside our companies, right? So how do we put in place a data architecture strategy that helps us deal with structure? I think the fundamental problem that we are going to be dealing with in this new AI gold rush is data and data structure. Everyone knows that data is the lifeblood of most digital companies. Everyone knows that data is at the heart of AI. But for us to put that AI on the shop floor, whether it's insurance or manufacturing, and have it be able to really generate profitability, to really reduce operating expenses, we need to feed it good data. That goes without saying, but what does good data really mean? And that's what I want to talk about today. There's a book written, co-authored by Daniel Kupal, who, if you had the chance to see this morning, his data modeling session is wonderful. I'm going to lean heavily on this book and steal heavily from it for the duration of this presentation. There's something that works really well. Those of us that have been involved in application delivery and app development, we know that domain-driven design is our friend. It helps us manage complexity. We don't eliminate the complexity, but we help manage it better. And one of those things that Daniel has mentioned inside this book is the concept of bounded context. There's a great definition that the bounded context is about managing the complexity of a system by breaking it down into smaller, more manageable pieces. And if you're like me, you get overwhelmed sometimes with data. You get overwhelmed with lots of new concepts. And it's we're all going to feel overwhelmed in this new AI gold rush at some point about something. And I think we can lean on these things that work well in application delivery, and one of those is the bounded context. If I apply this to the insurance space, and we can do this with any organization, but if I apply this to the insurance space, I know that the enterprise is really just a grouping of bounded contexts. I have sales and underwriting, I have customer, I have product, I have billing, I have claim, and all these different areas of the business, they need to work in unison with one another at some point. And so we're going to go from all the way to the top of the enterprise today, and in the next 25 minutes or so, down into some of the lower weeds and down to the data objects of one of the more compelling new use cases that's emerging in insurance. And so domains are important to us because domains fill these bounded contexts. So the first concept is the bounded context itself. The next concept is the domain. And a bounded context could be something like customer. I have Liberty Mutual. I came from Travelers, but I have Liberty Mutual for my auto and home insurance products. I love them, by the way. I opened their application, their mobile application the other day, and I decided that I wanted to reference it today because they've got a customer-facing application, and it's very basic. I can see the policy that I have with them for my auto and my home. I can see my billing information when my bill is due. I can see other products and services if I want to order them. And so this is kind of interesting because this is the customer context. I am the customer, and in the context of customer, I'm dealing with a handful of domains. I deal with customer, obviously, who I am, my address, my emergency contact information, but the policy information that I've purchased, the policies that I've purchased from them come from the policy domain. And I know inside Liberty Mutual that the customer domain and the policy domains are separate application delivery teams, separate systems, separate concepts. But to me as the customer, none of that matters. I open the application and then there's my policy. And the customer application that they built with mobile went to the policy domain, fetched the policy information for me, rendered it onto the mobile application. And the same with claims. If I file a claim, I can see my claims and my claim history. And so I put this on the screen because I think this is kind of important because some domains are shared by multiple contexts. And this is a really important concept when we talk about machine learning because we've been doing this really well on the app delivery side for a decade or more. We share information across development teams and across APIs. We build APIs that anyone in the rest of our organization can call if they need our data. And when we do that inside of a domain, we create a common model called the domain model. And this is really important for domain-driven design because it's something that is referred to the ubiquitous language for efficient data processing, right? I have to use a common datum language. When I build an API, I have to let folks in the rest of the organization know when you want to call my API, here are the inputs, here are the expected outputs, here's how this API works, and here's what it is. And I use a certain schema. And that applies to applications, that applies to the APIs and the events that underpin those applications. That also applies to the operational data platforms, the databases that store all that information. And so if we've been really kind of benefiting in the app delivery space from domain-driven design, which embraces bounded context, which embraces domains, and those domains have common shared information models for data processing, well, why can't that domain model also apply to analytics and reporting? Why is it that when I look at the data at 5 seconds old, it looks completely different than when I look at it when it's 5 weeks old? Well, it's traversed the great data equator in our organizations. It's gone from transactional through an ETL pipeline, perhaps, into the analytics space, and it's been messed with. Somebody has done something with it. It's not the same as it was in the transactional space. And this is the first, in my opinion, the first violation, if you will, of domain-driven design. And again, if I want to be fast with data processing and efficient with data processing in this new AI gold rush, not only, in my opinion, is it a problem that the data looks different at 5 weeks old than it did at 5 seconds old, there was a tremendous amount of effort expended to make it look different at 5 weeks old. And all of that data processing and data transformation is intellectual capital that I'd want to redirect to help us leverage those AIs on the shop floor better. AI is going to require a tremendous amount of developers. There will not be enough of us. If any of us are in the room, if any of you are afraid that our jobs are going to go away because of AI, absolutely not. Your role as a developer will change, but it will not go away. You're going to have to work with data. You're going to have to stitch data sources together in new and different ways than before, but there will not be enough of us. And so if that's the case, I want to apply all of our effort and all of our energies into unifying these two disparate worlds, transactional and analytical, and to say that, you know what, I really want to treat data as a product. If I want to treat data as a product, I care that it looks different at 5 seconds old and 5 weeks old. And I want to ask the question, why does it look different? Should it look different? I don't think it should look different. And obviously, this common model should be used in machine learning platforms. So now at the very end of the chain, we've transacted in an operational data store. We've ETL'd that into a data warehouse. Data scientists have probed those data stores, pulled the data out and massaged it, cleansed it, deduplicated it, put it into a feature store, and another copy of the data is now created, and I'm training data from that. Well, the machine learning model platforms, in my opinion, should be using the same corpus of information that the transactional systems are going to use. So I want to arm folks today with sort of a dialogue and a data architecture conversation to start. We're not going to solve this overnight, but we can start having this conversation about what it means to unify the transactional and the analytic spaces to kind of harness the power of our intellectual capital and our data processing efforts. So in domain-driven design, and this is sort of the nugget here, we use this concept of aggregates. That the domain-driven design model is, again, a way to break down the complex into more manageable pieces. And if that's the case, here's another example from Daniel's domain data modeling schema book. And he calls the aggregate identifying clusters of related objects and treating them as a single unit of change. Well, that's a one-to-one with the MongoDB document. If I have a policy and that has insureds, it has property, vehicles, and homes on that policy has coverages, it has deductibles, it has claims. Well, if all these things are kind of like-related, geez, I can store all of that like information into one MongoDB document. So if you have folks in your organization that are apprehensive towards MongoDB, if the word MongoDB or the word document raises people's concern and kind of makes the conversation tense, talk about aggregates. Because if you can get your folks to if you can get some of your business owners and some of your fellow developers who may not be believers in the MongoDB document model, we'll have a conversation about domain-driven design and talk about the power of aggregates when it comes to helping manage complexity. Right? We can all agree that complexity is not going away anytime soon. And aggregates help us manage that complexity better. And if you agree with that, then you kind of, if you can get folks to agree with the aggregate, you really kind of sold them on the MongoDB document without them knowing. On the left here is a typical insurance policy, multiple addresses, multiple insured items, and this is what I mean about the MongoDB document is essentially the aggregate. What I had to do on the left-hand side here as a developer is join 3 tables together to get the same result on the right. What I can do as a developer if I have that as a MongoDB document instead, less code, less work, less complexity. It's kind of a comical example. We have Bilbo Baggins here. His policy number is 3. His effective date is probably wrong here. It says final years of the 3rd age. He's got a couple of items that are insured in an array here. He's got an elven sword and he's got 1 ring. He might regret insuring that ring long term. And he's got an address here, 1 Bagshot Row, Bag End in Hobbiton. He has another address, the road, right? Because he's not always home. But this is a great example of the aggregate. Who wants to work with the left? Who wants to work with the right? I'd want to work with the right? It's less complexity. And in the age of machine learning and the AI gold rush, where we're just going to have to deal with more and more information has to be processed more quickly, I'm betting the farm on the right. Aggregates also introduce agility. More features, more business features can be served with one data object as an aggregate than they can if they were on the left-hand side in relational. And so data may arrive in many different sizes and formats. You may not be always collecting the full aggregate of information. You know, if I go to my Liberty Mutual application on my phone and I update my address, I'm updating part of the customer collection probably, but it's only an address change in that customer collection. If I update my emergency contact, it's a little array inside that aggregate. So the data doesn't always arrive as an aggregate, but when it lands and it gets stored, it's probably an update to an aggregate. And conversely, just likewise on the right-hand side, data that can then be served up in different shapes and sizes from that aggregate. So when we talk about the aggregate is not the end-all, be-all. It doesn't mean that you serve data up as an aggregate and you receive data as a complete aggregate. It comes in bits and pieces. But the aggregates introduce agility because one MongoDB document I can serve probably a dozen features from. I can serve a number of APIs from one MongoDB object, and that's not something that I can do with a relational set of objects. And so how aggregates enable AI, and this is sort of the question here, we kind of hear about MongoDB being good for AI. It's the data and it's the data structure. AI models are data hungry, and the information that we need to feed them is varied. Data scientists do a tremendous amount of data wrangling to be able to kind of massage and coalesce the data to a state which meets the model's needs. But the data has to come from somewhere. And if you're doing all this data wrangling work and you've got dozens of legacy source systems, you probably should be looking at aggregates. Because I can fold multiple systems into a single aggregate. My friends and I at the Travelers, we folded 20 policy issuance systems into 2 MongoDB collections. It's probably 30 to 40 years of Travelers information history right there. Data modeling and application development history. Folded into 2 MongoDB collections, 2 objects that folded otherwise, which was probably 50 to 75 tables. Can't remember now, but it was a lot. And so now if you want to now take that data and feed it to an AI, 1 to 2 documents versus 50 to 75 tables. I can build all my digital applications and services against that one aggregate now. Not only can I feed AI, but I can also point all my new apps and services against that single aggregate. I can load third-party data in. I can incorporate third-party data sources into that. They encapsulate source complexity. They provide curated single views for simplified and consistent access, and that sounds to me really familiar to what data scientists call features. I need a consistent and simplified view of the data to train the model. Geez, I want that as a developer for an API. It sounds like we're kind of on the same page without realizing it, even though we're in disparate, different organizations. And lastly, they act as ML features and can serve LLM prompt interactions. I'm going to get into that in the next few slides. That's the interesting part here, is that previously, a data scientist would look at the data warehouse and they would generate features from that warehouse. They would train a machine learning model from those features. Well, more and more now, what we're seeing with large language models don't need to be trained ahead of time. I can take a Hugging Face or an OpenAI ChatGPT model, and I can execute what's called in-context learning. I can ask it a question, and at the same time that I ask the model the question, I can feed it the data that it needs to answer that question. I don't need to train the model ahead of time on my data. I can feed it the data at runtime. So that says to me that more and more, AI is going to want runtime data, real-time data as features. And so then here, we kind of see the feature store on the analytics side and the transactional MongoDB collection almost kind of morphing into the same thing. This is probably my worst drawn out diagram today. Kind of looks like an airplane. And on the left-hand side, we have apps and services, all the business applications that we need to build. All the way on the right-hand side, we have AI and analytics, all the different analytics consumers, including AI of that data. But in the middle, that what I've drawn out in yellow here are really the data objects that I think matter the most and are going to matter the most in the next 5 to 10, 20 years. Aggregates, documents on the left-hand side in your cloud data platform, and then cloud object storage. Most traditional machine learning models are going to want to be trained from cloud object storage. Large language models won't care. They just want to be fed the information from wherever at runtime for in-context learning. But it just so happens that MongoDB documents and cloud object storage, in my opinion, are the most efficient use of cloud data processing platforms. I'm a little biased because I work for MongoDB, but I think if you're building a brand new application and you're creating an enterprise data strategy, the two things that you really, really want to look at are what is the database that your runtime applications are using to transact, and how is that data being stored for archive purposes, and that's object storage. And then with that strategy of MongoDB documents or aggregates and cloud object storage, I can build my entire enterprise AI data strategy from that. The next level down, I have ML features, right? And those ML features can be runtime from the documents themselves. Those ML features can be curated data sets known as features from data scientists. And then the next level down from there, we're going to talk in the next few slides about vector embeddings and files and objects. And so these two lines of yellow here are like the engines of an airplane, and we're all in the middle because our organizations are powered by data, and it's these data objects that I think are going to matter the most in the next few years. Documents, cloud object storage, vectors, and files. Relational Migrator, you heard a little bit about that today. So for anyone who hasn't seen the presentation on Relational Migrator, in my opinion, this is the fast path to aggregates. So we all have legacy data stores that we have to refactor. We all have legacy SQL objects. The three most compelling themes right now for the insurance industry this year are legacy modernization, cloud migration, and AI. And in my opinion, the first two are being dragged by the last. AI is pulling all of us into the right direction, forcing companies to address the fact that they've got legacy stores that need to be modernized, moving your data off premises into the cloud so you can have more elastic and efficient cloud computing to execute machine learning models. But Relational Migrator will help you identify your source schema, your target schema. So it's pretty neat. It's like, for any of you that used to use Irwin, you point Relational Migrator at your source SQL database, it sucks the schema in, it puts it onto a pane in front of you on a window, and allows you to kind of pick and choose. I want to take these three relational objects and I want to stream them into a target MongoDB collection. And then you can actually stream the data. You can do a one-time migration, or you can run a continuous migration in production, like a CDC job. So this is your fast path to aggregates. So I can start actually moving the organization into the direction of an enterprise aggregate data strategy with Relational Migrator. But I want to talk about a few use cases. We have about 6 minutes left, and I want to talk about a pretty compelling use case. This painting is from probably one of the most prolific artists in art history, Hokusai. But I like this one because as an insurance guy or a former insurance guy, it looks nice. It looks like these people have a nice little community here. I see some houses, I see some boats, I see some waterfront property. I see waterfront property. I see the potential for natural disaster here. I see the potential for a lot of property loss. And we say this, but we're in the midst of tremendous volatility from storms. We saw it last night. We've seen it across the US. We see wildfires, we see flooding. I don't think this is going to let up anytime soon. And as an insurance guy, it kind of breaks my heart a little bit to see insurers pull out of certain states like California and Florida. Because like those folks in that painting, they love their community. And there's one thing that I know that saves us all is insurance. We say this kind of jokingly, but good underwriting saves world economies. It helps us rebuild. It helps us pool our resources so the few that are impacted are supported. And so for all of us kind of in this industry or thinking about being in this industry, natural disasters are going to be a tremendous challenge for us going forward. In 2022 alone, we were 76% above the 21st century average in terms of natural disaster losses, just losses. But there's two really interesting statistics here. Of the $313 billion in losses in 2022, insurers only covered 42% of that. That leaves a 58% coverage gap. That leaves a lot of communities and a lot of us potentially uninsured or without options for insurance. And so one of the more compelling use cases that we're working on, I can't tell you the insurer, I can't really say anything about particular customers because you guys are also private. This is all secret sauce in insurance. But it warms my heart to know that these things are being built. So if we look at catastrophe claim processing, right? So a storm rips through a community and damages people's homes or God forbid, puts people out of their homes. If I look at it from a data architecture perspective, there's a few things that I know. Whether you're a claim handler out in the field or whether you're a customer with your phone taking photos of your own damage and sending in a little typed up description, there's a couple things that happen in CATs, or as the industry calls them CAT. Sometimes we get a flood of information. There's text, data, there's images that get streamed in, there's video potentially captured, but it's a massive sudden influx of data. Highly unstructured, right? This is data that doesn't have metadata around it. An image doesn't have metadata. Text notes that somebody types in about the damages. Claim adjusters who are out there in the field who, in times of tremendous amount of damage, they don't have the time to type, so they just dictate on their phone. They go from one house to the next, and they capture the damage. All of this data comes in suddenly and is highly unstructured. And so one of the things that insurers struggle with is efficient claim processing in one of these natural disasters. We can't get claims paid on time, people can't rebuild, or the cost of data processing is so high to the insurer that they decide they want to leave the market entirely or leave an entire market, vacate it. Well, there's a solution, and it starts with vectors. And here's where AI starts to kind of transform insurance and really starts to transform what's possible. So vector embedding, one thing that I know, we need to create vectors of the content, right? So if I can take text, a text blob, or if I can take an image, or I can take a video, and I can assign mathematical representations to the objects in the picture or the text from some notes that were either dictated in or sent in from a customer perhaps, that now becomes searchable. So the first thing that happens with vector embedding is the content comes in, but I've already got structured data associated with that claimant or that claim. So when I capture the unstructured data now, if I'm using MongoDB, I've got the claimant and the claim itself, and now I've got the images and the text notes that came in. I can vectorize that. That gets stored inside the MongoDB collection alongside the structured metadata. And the third thing, now I can search that. If I can process one claim and I have vectors associated with that claim, I can now search for like claims, claims that have similar types of damage, either from the note, I've inferred that now either from the notes or I've inferred that from the images potentially. Now, as an insurer, I can look across the entire disaster and kind of extrapolate and say, well, all of these potential other properties have like damage. So now I kind of understand the amount of liability that I have, the amount of exposure that I have. I know how many claim handlers I might need to send out into the field. I know the data processing that's in front of me now. You don't need a large language model to use our vector search. You can, but the first thing, once you load your structured data into MongoDB and you vectorize it, that gets instantiated into a Lucene search index. And as we know with MongoDB Lucene, if we want to use Lucene versus the collection, we just use a $search query. We write an aggregation pipeline query that starts with $search, and that points me to the vector store. So now that I've captured vectors alongside my claim, I can now search those vectors and I can find like claims. I can group them together and I can say, you know what, okay guys, you are the claim handling unit for this type of damage. I can do it with another type of claim, another type of damage, and group them all together and say, okay, you are now the claim handling group for this type of damage. I don't need a large language model for that. I can use a large language model, but I don't need one. But the real benefit to the large language model now is that I can feed those vectors and that structured metadata into the large language model at runtime with what's known as in-context learning. And I can ask the large language model probing questions about the corpus of data. And so in potentially minutes from ingest to storage, I can start asking probing questions of that data and dramatically reduce the amount of processing time. So I can have a sudden influx of note and video and photo data come in for a large catastrophe, and I can process that very, very quickly without hiring an army of data engineers to try to move that somewhere and structure it. This is a little bit of what that data architecture looks like. I'm running up against the clock. I'm going to show you 2 more slides. For claim processing in MongoDB, on the left you see the MongoDB collections. On the left you also see the kind of claim vector indexes that got created for that solution. On the right-hand side you see cloud storage. And again, the data processing platform and cloud storage. Where's your online database? What's your cloud storage? With these 2 technologies, I can solve any problem in insurance for the foreseeable future, in my opinion, from a data storage perspective. I can also weave in other assets if I have them. Like if I have claim handling guidelines and I want to hire an army of temporary workers and send them out into the field, and they can get a set of claims to process, I can actually serve up the claim handling guidelines to them. I can say, all right, now that I have textual descriptions from either the claim handler himself or the customer, him or herself, I can take that note data and I can then search to find relevant claim handling guidelines pertinent to that exact claim. And I can attach that to the claim record, so when somebody goes out there in the field and goes to a customer's door, they've got the damage assessment, they've got the actual claim handling guidelines right there in front of them and on application. And again, cloud storage and MongoDB, I can solve that problem with 2 pieces of technology. I can ask these 3 questions. What damages exist on that claim? Find me relevant claim handling guidelines and forms. Outline resolution procedures. And this is just a brief example, a small example, but this is how, in my opinion, AI is starting to transform insurance, but more importantly, why the data structure matters so much and why we should be looking at data and data structure, not the AI models necessarily. We'll leave the AI models for the smart folks, for you folks, not myself. We built another insurance demo. There's a little QR code if you want to look that one up. It's kind of unrelated, but it's about streaming data from connected cars into MongoDB time series, making automated underwriting decisions off of that data in real time. There's a QR code up there. One last slide here. You can throw me off the roof at 5:30 if you want at the rooftop bar, or you can leave me your candid feedback here. I'd love to hear from you folks. So I'm out of time, but thank you so much. Thank you for letting me share these slides with you folks.